Hi, welcome to this episode in which we will continue analyzing our BCI competition dataset, and in this video we will be looking at how to perform time frequency analysis using lively vectors and functions from FieldTrip, and we will see how we will be able to visualize our time frequency results in a similar way to that of the ERP analysis, and later on we will see how to correct for multiple comparisons and check for clusters. Okay, so let me start by running this part that we have seen before until we reach this line. And in this one, what I was doing, I was specifying a baseline period in which I felt like this could be a part that doesn't have any activity. So let me step over this, and I specified this as 3. So I'm basically looking at 3 seconds before the stimulus. So that's why I took our onset variable, and then I looked back in time 300 samples from that onset, before that onset, and then I'm doing the same trick as I was doing with the data, where I repeated the data and I cut my time of interest. So feel free to check this part when we segmenting our trials. And then I took these onsets, and then I kept increasing the indices after this line. So we would see that they are linearly increasing with the steps of 1. And then I just was accessing the data in the same manner. And what I was doing here, I am here concatenating my data of the baseline with the actual data, and I'm doing this in the third dimension, which is time. And then we can look at the results of this, such that we can see now that we have concatenated the time dimension. So it should be around 700 data points. So we can proceed with this and see that our trial, yes indeed. So now we have the baseline. After that we have our actual trial. So after doing this, I'm just defining the beginning and end of the baseline periods and stepping with 1 over the sampling rate, as we always do. So I'm stepping from taking from -3 until just before 0, because I'm considering 0 to be the beginning of the trial, and I'm considering this to be within the actual trial time. So I'm here extending the time to include the baseline. So now we are starting from baseline and ending at the end of the trial. And after doing this, we can check our data and see that now the time is including all the time information, and the data the trial is also including all the time information with the baseline. And we have this variable baseline just to specify the baseline period. And then we can enter our LVTF, which is the time frequency analysis function that we will use. So here I'm just printing time frequency analysis that we are performing, and here doing the same thing as with the ERP, where we just checking which inputs the user specified, and then we assume some of them. Okay, and here we are checking if we have a topography, if we have a layout. If we don't have a layout, I'm gonna load the layout that we have by default, and then here I'm checking whether the data is in the golden tensor in the 3D. And here we are interpolating our channels, and then we are looking at the layout here. So here I'm just loading my layout, this huge layout. It has a lot of channels, and then I'm checking which ones I have here. So which channels do we have? Because we have only 12 channels, I will be choosing some of these channels. You can see we have many channels here, 76 channels. So I'm just gonna choose the channels that we have. So we have 12 channels, so that's what I'm doing here. So I'm checking whether I'm just changing this to lowercase, and I'm checking the index of each of the labels of the 12 channels where it does exist in this huge label struct. So we can see the index of each channel and store it in channel ID, such that we will have 12 IDs, and each one of them is the location inside of this reference layout. And then I'm just cutting the reference layout such that it will only include our 12 channels, so that we can see now they are 12. And here I'm doing interpolation. So here I'm doing interpolation similar to what we did with the ERP analysis. And the reason I'm doing this is that I want to map the actual positions that we have here to normalize the positions that we can plot on the screen, such that we can see the topography and see the actual time frequency analysis for every channel and its corresponding location. So right now we have the normalized indices, and we can continue with this. Here I'm checking the conditions, that we have two conditions, and then I'm doing the time frequency analysis. So I'm doing this for the first condition and then the second condition. So I'm just checking which triads correspond to the first condition and which ones to the second condition. And then we can enter this function so that we can see how to perform our time frequency analysis. By the way, I'm here doing both time frequency analysis and intertrial phase consistency. But here with this intertrial phase consistency or coherence, I'm gonna leave this for a separate video just to discuss this in more detail. So here I'm specifying that I need power. I'm doing time frequency, I need to plot power, and here we're using only channels, and this is a multitapper method. So the basic idea of the multitappers, just very briefly, is that instead of looking at an effect that might not be perfectly time looked and phase looked to your stimulus, so the idea is that if you have something in the first trial that looks like this, and in the second trial like that, and the third trial like that, if you are averaging all of this effect time point by time point, you would get something like this. And the issue with that is this: if you have very small jitter between your trials, you are going to lose the effect when you are getting the average of all trials. So what the multitapper method is introducing is something like this. We are going to use a lot of tappers, and each of them is different, so almost like that. And I'm gonna multiply my signal with every tapper of these, such that each one of them is like exposing something different than the other one. They are actually orthogonal to each other. So anyway, they are showing something different from one another. So for instance, if we use this first tapper to tap our data and just multiply this tapper with our data, it will show the effect that is here. So if we took this tapper and put it on top of our signal, it will show the effect that is here, okay? And the result will be almost like that. And then we take the second tapper and we tap our data. So what we'll do, we'll multiply this second tapper with our data, and it will just magnify the effect here and the effect there and attenuate these parts. So it will show perhaps something like that. Okay, and our third tapper, and we also multiply it with our data and see the effect of this. And then what we do, we will end up with data that is now tapered, and we go ahead and we can get the Fourier transform for each one of them, so that we now know that our single signal is now tapered with multi-tappers, and each one of them is showing different behavior or showing interesting characteristics that are different from the other one. We can do a time frequency analysis, or we can do FFT, fast Fourier transform, on each one of them, and we can see what will be the result of that. So we can look at the spectrum, and we can see the effect that we will get in frequency. And this is good because right now we can see the effect that we have for each of these tapered signals, and then we can sum all of these and get one frequency spectrum. And the good thing about this, it will act as like magnifying the thing that was really consistent in frequency, such that if it is not really very perfectly time looked to the stimulus, it would still appear in the frequency domain, which is good, and it might just smooth other frequencies that were not very prominent in our signals. So that's very brief, I know, but it's just the main idea of that. And here we are using Hanning, so it's almost looking like this tapper, and we are just moving to the next line, so we can specify our frequency of interest, and we here specifying from the first frequency until the end frequency, from 1 Hertz to 30 Hertz. That's my frequency of interest that I used here, and I'm stepping with 60 points, so I have 60 points between 1 and 30, such that we will go from 1 to 30 and we will have 60 frequency points. And with this line, it's actually a nice line that we can adaptively specify our frequency as we go up in frequency, and we're estimating higher frequencies. We can do like a combination of our time and the frequency to know how much data points we would need to estimate each frequency. So as a general rule, you would need like 3 or 5 cycles to estimate a frequency very well. What does this mean? So let's say that we are trying to estimate 1 Hertz, which is our first frequency. What is the meaning of 1 Hertz? 1 Hertz means that you are completing one, if this is 1 second, you are completing one cycle, one full cycle in 1 second. Okay, so to estimate this frequency very well, of course, on the unit circle, this means that there is a vector and it's completing 2 pi in just 1 second. That's the other meaning of this if we look at vectors. Okay, so as a general rule, we would need this vector to rotate like 3 times to complete 3 cycles, okay, or 5 cycles as a minimum, in order to be able to estimate the power very well. The power is the square of the magnitude, so to estimate the magnitude of this, to estimate our power and other measures in the frequency domain, we would need at least 3 or 5 cycles. So what does this mean? It means that if you are looking at time and we know that our frequency is 1 Hertz, so it's completing 1 cycle in 1 second, then we would need 5 cycles of this. So we would need 5 seconds to estimate this frequency. So we'd really need 5 seconds to estimate this particular frequency with certainty to some extent. Okay, and then we can go to the next line and see that we here specifying the time of interest, and I'm here keeping the full temporal resolution of our data, so I'm keeping all the time points, and you can play with this and change how your data will look like. It doesn't make a huge difference. Of course, it's up to what you are doing, so yeah, it's changing according to the application. And then we can go to the next line, which is pad. Over here are zero padding our signals when we are doing a convolution, and we have talked about the Fourier transform, and here we can do time frequency analysis with different methods actually. So we can do this with wavelets, we can do this with moonlit wavelets. So they look something like that, okay, and you can think of them as having a complex sine wave that is like multiplied by a Gaussian mask. So it's almost like having a Gaussian kernel, and you are multiplying this to your complex wave that we have seen before. If we looked at the real imaginary and progression in time, we would see that this is cosine, and this is sine, and this is progression in time. So we are looking at cosine, and we are looking here at I sine, okay, and we can say that this is a complex signal, and we can then taper the signal or apply this kernel of by using a Gaussian, and it will look something like this. So these parts will be attenuated a little bit, and here we are just plotting like the real part of the moonlit wavelet. The main idea is that this wavelet is having a particular frequency. By the way, if you don't know what I'm talking about here, please check the video about the Fourier transform, where we discussed this in detail and we showed an animation for this. So after putting this moonlit wavelet on a specific frequency, now we have an oscillating a wave. It's a rotating vector on a specific frequency. So we can now take this, and let's assume that this is 1 Hertz. This is put on 1 Hertz. So we can then take our EEG signal, which might look like this, and we can apply a sliding window approach. What we mean by this, that I'm gonna take this wavelet and I'm gonna put it here, okay, and I'm gonna multiply element-wise, multiply all of my wavelet, the length of the wavelet, with my data, and then I'm gonna sum all of this, and I'm gonna take the summation of this, and I will have a new point, a new value, okay. And with the sliding window approach, I will just proceed by shifting this. I will just slide my wavelet, so instead of starting here, it would be starting here, okay, and then I just multiply it again, get the sum of this, which is, of course, this is the dot product, and get the second point, and keep sliding this again and again and again, and every time we do a dot product and we end up with a value such that we will be building our new signal after applying this moonlit wavelet kernel, such that we will know the time resolution of this new signal, okay, and we know that the frequency was 1 Hertz, okay. So this is more like a row in our time frequency plot, because the time frequency plot will look like that. Let me draw time frequency plot. So this would be time, this would be frequency, and here you have power, or you have something else. With the time frequency plot, we would have power here. So after you are sliding with this moonlit wavelet, which was on 1 Hertz, you know that this is the frequency of 1 Hertz, and you would have this value, and it will be color coded in this row. And the thing is, you can just now change your wavelet to 2 Hertz, and you estimate the second frequency and put the second row, and so on until you finish all frequencies, and then you will have your full time frequency plot.